Okay, this is going to go over chapter 2, our chemistry chapter, objective 5, where we talk about the difference between atoms, ions, and isotopes. So I know we left off with our story about having an unhappy sodium and an unhappy chlorine atom, and we will get back to that, but this objective is going to talk about atoms, ions, and isotopes before we move into figuring out how to deal with the sodium and the chlorine. Okay, so let's redefine again what an atom is. So this should be not new information. This should be a review. Atoms, like we've said previously, are electrically neutral, which means they have the same number of protons as they have electrons. As you can see for sodium right here, it's got 11 protons and 11 electrons. Now, we know that while it's neutral, we also know now that it's unhappy because it doesn't have the right number of valence electrons. We will get back to that. Now, all atoms, like we said previously, they actually want 8 valence electrons, and we know sodium only has 1. Atoms that do not have 8 valence electrons, what are they going to do? They're actually going to gain electrons, they're going to go get some more, or they're going to lose what they have until they have the 8 that they want. So sodium, again, very unhappy. Chlorine, also very unhappy because neither one of them had 8. But we'll talk about how they're going to handle that in a little bit. Now, let's talk about the definition of an ion. This is a new word. We haven't talked about this yet. Ions are charged particles. That means that atoms that do not have 8 valence electrons, like we said, are going to either gain or lose electrons until they have 8. Now, when you start changing that electron count, they're no longer going to be neutral anymore. So when that neutral atom gains or loses those electrons, so it has 8 valence electrons, it will form what's called an ion, because again, it will no longer be neutral. There are 2 types of ions. You have cations, which are positively charged particles, and then you have anions, which are negatively charged particles. This is a little more than we need to know for this class, but I'm going to go ahead and kind of just show you what we've got going on here. You have a neutral atom, which for the most part, all atoms, while they're neutral, they're not happy because they don't have 8. There's an exception. The last column on your periodic table, if you look in your packet of papers there, you had a periodic table. If you look at that very last column, helium, neon, argon, krypton, xenon, radon, they already have their full valence electrons. They've got their 8. I know helium's an oddball there, but we're not going to worry about it. But they're noble gases. They already have a full outer shell. They've got their 8 valence electrons. They're the ones that don't have chemical reactions with other elements because, again, they've already got their 8 valence electrons. They're neutral. All the other elements on the periodic table, while they're neutral, they're not happy because they don't have their 8. So when a neutral atom gains electrons, it's going to turn into an anion. When a neutral atom loses electrons, it's going to turn into a cation, a positively charged particle. Keep in mind electrons are negative, that's why it's kind of weird. So all you need to know is that neutral atoms gain or lose to form cations or anions, okay? So question number 12 in your in-class questions, I'll give you a second to take a look at that. What happens when I'm writing backwards? Okay. Atoms are electrically neutral, positively charged. Particles are called cations. Now, one way you can remember that is because cations is spelled with a T, which looks like a plus sign. And if that helps you remember cations are positive, then, you know, whatever little tricks we can figure out to help us do well on the test and memorize this stuff. So another thing that, if it helps you remember, we've got these cations, which are positively charged particles. Again, a little bit more information than you need to know to get the joke, but for the test anyway. So 2 atoms walk down the street. One of them says, wait, I think I lost an electron. The other one says, are you sure? And then Yes, I'm positive, because what happens when you lose an electron? You become positively charged. Again, a little bit more than we need to know for our test, but still cute. So question number 13. What I'd like you to do is look at the symbols there and tell me whether you're looking at an atom, a cation, or an anion based on the symbol. Okay. So if you remember back in one of the previous videos, we mentioned when you're looking at a symbol, pretend like it's in a box. I'm just going to use X as a generic symbol. And the information that you're looking for is in the upper right-hand corner. That right there is going to be where, if there's a charge, it's going to be located there in the upper right-hand corner of the symbol. Now, you can see for sodium over here, there's nothing up there. So you're going to go ahead and say this is an atom. It's electrically neutral because there's no charge listed. So that's how I knew this was an atom. Now, phosphorus with a -3 charge, the only thing I'm interested in is that negative sign right there. I don't care that it's a -3, a -2, a -1. It doesn't matter. The bottom line is, hey, this is a negatively charged particle. It's an anion. Number 3, again, all I'm interested in is that plus sign right there. Don't really care that it's a +2 or a +1 or a +5. It doesn't really matter. It's a plus sign, therefore it's a cation. And number 4, you may notice, well, it looks a little different. It's not really an element. And you're right, it's not. It's called a polyatomic ion. So you're not going to find capital O, capital H anywhere on the periodic table because it's not there. It's made up of 2 atoms, or 2 elements, oxygen and hydrogen, so it's a little bit different. But again, it doesn't matter. The only thing I'm interested in is that negative sign, and that negative sign tells me this is an anion. Why did I put that one there? Well, this one's going to actually come back and revisit us a little bit later on down the line in this chapter. This is a polyatomic ion called hydroxide. OH-1 is the hydroxide anion. And it's important when taking a look at the pH scale, which is one of our objectives for this chapter. Anytime you have a lot of hydroxide ions present, then you know that this is a base, B-A-S-E, on the pH scale. Okay. So when we're looking at sodium, we said that our sodium atom does not have 8 valence electrons. It only has 1 valence electron. So we know that the sodium atom is very unhappy, and in order to fix that, the sodium atom is going to gain or lose electrons. So you kind of think about it this way. I'm not going to ask you to look at an element on the periodic table and tell me whether it loses or gains electrons. I just need you to know that sodium only has 1 and it wants 8. It's easier to lose 1 thing than it is to gain 7 things. In order for it to have 8 on this outer shell, if it was gaining, it would have to gain 7 more electrons. But look what happens if it loses this electron right here. We drop one of those energy shells, so it completely disappears. When the electron goes, the energy shell drops to the next one. And if you look, energy shell number 2, orbit number 2, has got 8 valence electrons in it. So if we lose that outer electron, we default to that energy level number 2, which has 8. Now, because we lost a negatively charged particle, we are now an ion. So we are now we're positively charged because we lost a negatively charged particle. And this is an ion. We no longer have an equal number of protons as we have electrons, so we are an ion. Now, chlorine is going to do the same thing. If you remember, chlorine only had 7 valence electrons, so again, it was also very unhappy because it wants 8. And in order for chlorine to get 8, is it easier to lose 7 on this outer ring, so it'll drop to that second orbit, or is it easier to pick up 1 electron somewhere? Well, it's actually easier for chlorine to gain 1, so if you notice, we keep that 3rd energy level, but now we have 8 valence electrons as opposed to the 7 that we had originally. This is a happy sodium ion. We picked up a negatively charged particle, so we're now an ion, but it's a happy ion. It's a happy charged particle because it's got a full 8 valence electrons in that outer shell now. Now that we have all of these atoms on the periodic table that have either gained or lost electrons so that they have a full outer shell, with the exception of that last column, the noble gas column, we are left with a bunch of ions, a bunch of charged particles. And if you all remember, opposites attract. So there's an electrostatic attraction between the positively charged particles on the periodic table and the negatively charged particles on the periodic table. I thought that was just a cute little graphic. Okay, just kind of taking a little bit of a break from that, we need to kind of go over the symbol again. So again, pretend like you have a symbol in an imaginary box, and each corner of that box represents information. We've already talked about how the charge is going to be found in that upper right-hand corner. But what about the other corners of our box? What does that represent? The upper left-hand corner is going to tell you the mass number. The bottom left-hand corner is going to tell you the atomic number, which again is the same as the number of protons. Now, if you remember, the symbol, such as hydrogen, and the proton number for hydrogen, which was 1, that's the same information. That's redundant information. If you know it's got 1 proton, then you know it's hydrogen. If you know it's hydrogen, then you know it has 1 proton. So a lot of times the atomic number isn't written because it's understood. If you know the symbol, then by default you know how many protons it has, because those two cannot change. The bottom right-hand corner right here tells you how many atoms you have of that particular element. So let's look at some examples here. So here we have oxygen. Now, if you notice, the proton number for oxygen is 8. That's not going to change because it's oxygen. Okay, it's going to have 8 protons. I don't care what else is going on with it, the proton number is the same. If you see a number in the upper left-hand corner, this is the mass. So this particular oxygen has a mass of 16. This particular oxygen has a mass of 18. Now, if you remember the definition of mass, mass is the sum of the protons and neutrons found in the element. Well, if it's oxygen, we know it's got 8 protons. So in order for the mass number to be different, what had to change? It couldn't be the proton number that changed. So what's the other particle that makes up mass? Neutrons. So while yes, these are both oxygens, they have different numbers of neutrons. They can't have different numbers of protons because they're both oxygen. So the only other thing that could be different with them is the number of neutrons, which will affect the mass. Remember, neutrons contribute to the mass number. So you represent that by having a number in the upper left-hand corner. Another example, if we look over here at, again, oxygen, we have oxygen, the anion with a -2 charge, and we have oxygen, the atom, right here. Now, what's the deal? How do we know this is an atom? Because there's nothing written up here in this upper left-hand corner, upper right-hand corner, I'm sorry. So this is the atom of oxygen, and this is the anion of oxygen. Now, if we take a look at a molecule, for example, like water, H2O, the number at the bottom right-hand corner of that symbol is telling you how many of everything you have. So that 2 is going to let you know you have got 2 hydrogens. So the number that comes after tells you about the symbol before, right? So that is telling you have 2 hydrogens. Now, how many oxygens do you have? Well, there's not anything written there, so it's understood that if it's present, well, you got to have at least one of them. So you actually have 1 oxygen, but again, the ones are not usually written when you're looking at elements like that, symbols and formulas. So question number 14, how could I ask the question on the test? I'm going to give you a picture, something like this, and ask you to just tell me what everything is. So I'll give you a second to take a look at that from those in-class questions number 14. Okay, so the 11 tells you the mass. Remember, that's the sum of the protons and neutrons. -3 is the charge. This is an anion because it's negatively charged. And number 5 represents the number of protons that boron has. Now let's take a look at isotopes. So we've talked about atoms already. We've talked about ions already. Now let's take a look at isotopes and talk about them and their definition. So why did I put a bag of Skittles on our picture here? Well, as you know, when you eat a bag of Skittles, they all have different like fruity flavors, but you could tell if I slid in like an orange M&M, you would definitely know that is not a Skittle. So while Skittles, they all have they all have similar characteristics, they're different in the fruit variety that you taste, right? So isotopes are very similar. They're different kinds or types or varieties of atoms. The only difference is isotopes are different in the number of neutrons that that atom might have. We saw that previously with oxygen in the previous slide. So let's just kind of take a look at this. We've got two different pieces of information here giving you two different ways to give you the same information. So this right here is what's known as the atomic symbol. When you look at this, you see magnesium with a +2 charge. It's going to have 26 as a mass number, and it's got 12 protons. When you're reading text, this is how the information for magnesium is written. So when you're reading a paragraph in a textbook or a paper or something like that, this is how the magnesium information is presented as you read, okay? Now, on the periodic table, this is what you see. You see a table of elements. The symbol is going to be in the middle. The mass number is going to be at the bottom, and the proton number is going to be at the top. So, same information, but kind of depending on how what source you're looking at. Are you looking at it in text, or are you looking at it on the periodic table? It's going to be structured a little differently. So what we're looking at here is the atomic symbol rather than periodic table information, okay? Again, it's still the same thing. It's just you have to know what you're looking at. So this is in text. So what does this 12 up here mean for carbon, and this 13 up here for carbon, and this 14 up here for carbon? That is telling you the mass number. So what we see here are three different varieties of carbon, and they're different in the number of neutrons they have, hence their mass number is going to be different. Another way you could see it in text is carbon-12, carbon-13, carbon-14. Now, if you notice, why don't you see the proton number? Why is that not listed? So carbon right here, the proton number would be 6. Right here, the proton number would be 6. And right here, the proton number would be 6. Why don't we have the proton numbers listed? Well, because it's carbon. Of course we know it's got 6 protons. We don't have to put that down. It's easy. We all know if we're talking about carbon, the proton number is going to be 6. So what's different with these? If the proton number didn't change, then what did change to affect the mass? That would be the neutron number. So if you look inside the nucleus right here, you can count those 6 protons, but if you also look, you can count the 6 neutrons. 1, 2, 3, 4, 5, 6. If you take a look at this one right here, you can again count those 6 protons in the nucleus, but 1, 2, 3, 4, 5, 6, 7. It's got 7 electrons, which we knew because if you take 13 minus 6, the mass number minus the proton number, that will give you 7 neutrons. Okay, and in the first one we had 6 neutrons. And in the last one, we can go ahead and just do the math. 14 minus 6, that's going to be 8 neutrons. So the difference between each of these carbon atoms is the number of neutrons that they have. Everything else is the same. These are called isotopes. So I'm going to let you do 15 on your own. The big takeaway was kind of what I just said. It was the neutron number. Everything else is going to be the same. So carbon-12 is going to have 6 neutrons, carbon-13 is going to have 7 neutrons, and carbon-14 is going to have 8 neutrons. These are all represented of isotopes of carbon. Now, when we change our neutron number, notice carbon-12 only has 6, where carbon-14 has 8. Notice what's happening with our nucleus here, because these neutrons are in the nucleus. So what this right here tells us is our nucleus has 12 particles in it, right? That's our mass. It's got 12 protons, 12 neutrons. The nucleus mass here is 13. It's got 13 particles. And then carbon-14, well, there's 14 particles in the nucleus, 6 of which are protons, 8 of which are neutrons. Now, the nucleus of an atom can only hold so many particles. Think about it like an elevator. When you get in an elevator, there's a max capacity on that elevator. It can only hold so many people. Well, a nucleus is the same. It can only hold so many particles. Once it gets too many particles in that nucleus, it is very upset. So carbon-12 it's fine with 12 particles in the nucleus. It's quite happy nucleus. Carbon-13, it's okay. It's still in the zone of it's pretty full nucleus, but it'll deal with it. Now, carbon-14, however, this one is a very unstable nucleus. It's got way too many particles in it. So what you're going to have to do, what this atom is going to do to alleviate the huge number of particles in the nucleus, is to start changing the particles that are in there and start throwing stuff out. It's got to get back to a stable nucleus. It's just got too much stuff in there. So an unstable nucleus is what's going to form a radioactive isotope. So we've got our 3 isotopes of carbon, but carbon-14 is considered radioactive. The other two, 12 and 13, they're stable. So the reason why it's radioactive is because it's got too much stuff in the nucleus. So this right here, while it says a radioactive atom, this is actually the nucleus of that radioactive atom. We're not really worried about the electron cloud here. And this has just got too much stuff in the nucleus. So what this is going to do is start chunking out energy, high energy particles, which are damaging, and then chunk out other particles like protons, could chunk out electrons, could, again, it's trying to get stuff out of there. Yes, I know it can chunk electrons out of the nucleus. It can change what's in the nucleus and start throwing stuff out, such as even electrons. So radioactive isotopes, also known as radioisotopes, are atoms that contain an unstable nucleus. Unstable nucleus will spontaneously emit radiation such as alpha particles, beta particles, and gamma particles to try to become stable. Now, you don't have to know this list. I just put this up here to show you why we have to know that radioactive particles exist. They are used in medicine. If you're going into the nursing field, you're going to end up running into stuff like this because you're going to be using it for various things. Your patients will have been exposed to this. For instance, yes, there's even a carbon-11. That would be a PET scan type situation. Blood circulation, they'd use isotope for sodium-24. Thallium-201 for heart tissue issues. So again, different isotopes are used for different things in medicine, and these are radioactive isotopes, meaning they are a little dangerous, to be honest. Again, in PET scans, you talked about PET scans in the previous chapter. Why would they use PET scans with short half-lives, such as oxygen with a half-life of 2 minutes, up to fluorine with a half-life of 110, rather than like uranium? Well, uranium has a half-life of, I don't know, like 100,000 years, so you're going to be radioactive for a very long time. These, no sooner is the test done than you've already offloaded all of your radioactive particles, so you're no longer hazardous to other people. Again, you don't have to know that. That was kind of for your information, but I wanted to explain why we're learning these radioactive isotopes, and there is such a thing. So question 16, when an atom has an unstable nucleus, it is called... B, a radioisotope. And that's going to conclude objective 5.